Okay, today we're talking about Chapter 10, Section 4, compound interest. All right, so we've talked about interest quite a bit, and now we're going to just kick it up just a little bit. And let's do this. It's just more formulas. I'm pretty sure these are probably given to you. I actually haven't looked at your homework yet. They're at least they're given in like college algebra or something. Uh, but they're not too terrible to memorize because they kind of build on one another. We'll just jump straight to this. I don't think that table is too useful right now. Just going to put this here with example one. All right, so this section, much like last section, is it's plug and chug. Just figure out what your numbers are, what goes where, what variables, and then it's really simple from there. And of course, we'll um, you know try to take it slowly through this, but I don't think it's too hard. So let's just start at the top. So calculating the amount in an account for compound interest paid once a year. So if you deposit P dollars, so P is going to be dollars, at a rate R, so R is rate, and of course in decimal form, subject to compound interest, then the amount A, that's the amount of money in the account after T years. So we are told what every single one of these variables are. And looking at this formula, A is the amount after T years, P is the amount that we deposit in dollars, R is rate, and T is years. So using that, let's jump straight into example one. So example one reads, you deposit $2,000 in a savings account at Hometown Bank, which has a rate of 6%. Okay, so right away we are told what P is. We are depositing $2,000. All right. We are told has a rate of 6%. All right, in decimal form. Right. So we're going to put 0.06. That's all that the opening part states. But A reads, find the amount A of money in an account after 3 years, subject to interest compounded once a year. Okay, so we're told this is going to be after 3 years. So looking at the formula, all right, let's just go ahead and, for the sake of this, let's put the formula right here. And then we're going to put a little bit of a gap there, and you'll see why here in a moment. Okay, so again, this is our formula. All right, we're trying to find the amount. Again, looking at A, find the amount. So we're trying to find this. So that's going to be pretty easy. We don't have to do any sort of rearranging. All right. Well, if we fill in the blanks here, well, P we said was $2,000. Hopefully this will fit. All right. Our rate was 0.06, and this kind of ties into an earlier question, and I'll touch on that in a moment as well. 0.06. And then time, it says after 3 years, so we're going to erase actually let's put that in blue as well, just kind of stay consistent. And the time we were told was 3 years, and let's go ahead and put this up here. Time 3 years. And I'm going to move this over to the left so I can actually put the solution. Yeah, that'll do. All right, and let's do some quick calculator work here. And so what I was saying earlier about, I suggest, at least at this point, maybe put 1 plus this into your calculator. But the thing is, you could save yourself like literally maybe half a second, and instead of putting 1 plus 0.06, just put in 1.06 into your calculator, and that again, like I said, the time it saves you is so minute, but you know, I guess if you do a lot of these, they add up, huh? All right, raise to the third power, and then times 2,000. So 2382.03. So all this is equal to 2382.03. Alrighty. So um, that's A. We just found the amount, and B reads, find the interest. Well, the interest, the math here is pretty easy, right? If we started with $2,000 and we get up to 2382, well, the interest is obviously going to be $382. So again, all we did was just simply follow along with this formula. Again, it does help to point out what the variables are, but then after that, you just simply plug it in. And like last section, it doesn't really get much harder than that. All right, so this is pretty important actually. All right, so we need to figure out what some of these words mean. So starting at the top here, the period of time between two interest payments is called the compounding period. When compound interest is paid once per year, the compounding period is 1 year. We say that the interest is compounded annually, right? And if we do it twice a year, we call it compounded semi-annually. 4 times, compounded quarterly, right? And then we can also say something like monthly compounding. Semi-annual compounding is twice a year. Monthly, there's 12 months in a year. N corresponds to the amount of times that we not correspond. Corresponds to the amount of times that we compound in a year, right? So it doesn't. I mean, we could say, like I don't know, bi-monthly, right? Compounding bi-monthly. Well, that would be 6 times a year, right? Because you do it every other month. So the language here is precise, but you just kind of have to get used to it. Okay, so another formula. You've probably seen this formula before. At least, I feel like it's taught a lot in algebra courses, or at least towards the end of algebra courses. But again, it's just one of those that isn't too terribly difficult. Um, it's just simply the amount again is equal to P, and then of course, like on the previous formula, it was 1 plus, the rate, right? Well, now we're going to have, it's going to be 1 plus the rate over our n number of times that we compound. And that's realistically it. And of course, obviously, the exponent being nt. But it's a simple plug and chug as before. So let's go ahead and look at example 2. So it says you deposit $7,500 into savings. So let's go ahead and put P is equal to 7,500. Right, and a savings account that has a rate of 6%. So again, we'll put our rate as 6%, 0.06. Let's fix that. The interest is compounded monthly. Okay, so if it's compounded monthly, how many months are there in a year? Well, there are going to be 12. So we're going to say N is going to be 12. All right, and then A is wanting us to know, want us to figure out how much money will we have after 5 years. Well, 5 years, well, that's going to be T is equal to 5. Okay, so looking at this, I have 1, 2, 3, 4 variables solved for, and looking at the formula, I've got 1, 2, 3, 4. Did I mess something up? 1, 2, 3, 4. Oh, T. There it is. 5 unknowns. The T. All right. So we have four of the 5 unknowns given to us, and obviously that last unknown is A. So all we have to do is plug in all these values and figure out what A is. So A is going to be P, which is 7,500, times 1 plus my rate is 0.06 all over my N, which is 12. And let's just go ahead and do the math of N times T. Actually, let's not do that, just for the sake of really doing this thoroughly. All right. So all this, I just have to put into my calculator, right? So here we go. Um, all right. So we've got 10,000 Uh, $116. I guess we're going to cents. 37 or 38 cents. Okay. So that's we just did the compound interest formula for this particular problem, and of course it reads find the interest after 5 years, and again it's not too difficult. All we have to do is take my interest or what my bank account is now. I guess it's no what my savings account is. What my savings account is now, and subtract 7,500. And of course that's what we did on the previous page. It was just a lot easier on the previous example. It was a lot easier doing 2382, taking 2,000 from 2382. So we did that in our heads, and we can probably do this in our heads as well. But for the sake of this, we're not going to. Yes. Okay. Uh-huh. Okay. No, no, no. That's completely fine. Okay. Are you putting this into your calculator, or are you just wondering what it looks like right on this page? It's it is an exponent. I'm raising it to the power. Does that make sense? Are you familiar with that? Like three squared, something like that. All right. So what? Okay. That's fine. On your calculator, you might have a little caret like that. Do you have something like that on your calculator somewhere? Okay. Well, for the time being, let's not worry about it. We'll just add that into the things that we'll talk about after class. But yeah, it's just simply an exponent. Okay. Anyways, so if we want to find out what B is, find the interest after 5 years, I'm just going to simply take the amount of money that I have now after 5 years and subtract my original deposit of 7,500. Right? And doing that, it's 25, 26, 26, 16, 38. Right? So 26, 16, 38. And that is B. And of course, it's right in the middle of the page, but I don't feel like it deserved to get its own page. Right? All right, and we're already a third through. All right, so continuous compounding. All right, so continuous compounding is what it sounds like. We are compounding continuously. On the previous couple examples, we were compounding. I forgot what example one was, but example two, we were compounding every month, right? Continuous compounding, again, is what it sounds like. It's just compounding continuously over and over and over and over again. And for the most part, continuous compounding is generally what you would want. Of course, it depends on the interest rate, but continuous compounding because the way that compounding works, the more compounding you have, the more compounding moments you have, the the more the interest rates stack up. Right? But it's not always the case that it's the best. And let's go ahead and maybe we could. No, we'll just snip it like this. All right, so the textbook reads, some banks use continuous compounding where the compounding periods increase infinitely. As in, the number of compounding periods in a year increases without bound. The expression 1 plus 1 over n raised to the nth power approaches the irrational number e. This is illustrated in Table 5, which I didn't really snip. Um, yeah, I don't really need that. As a result, the formula for the balance in an account with n compounding periods per year, of course, this is just showing us how we get to our equations. So the formulas for compound interest. After t years, again, we're told what each of these variables are, so whenever you get to the problem, you just have to kind of connect the dots, right? So t is years, the balance, which is going to be A, or the amount, in an account with principal P, okay? Principal, again, is how much you originally invest or how much you originally put into the account. And annual interest rate R, again, these variables are recycled. They're the exact same variables that we've been using so far. All right, it's given by the following formulas. For n compounding periods per year, This is the formula that we just got done doing. All right, this is when we compound. The moments of compounding per year. And then continuous compounding is such an easy equation. A is equal to PERT, right? And where we using this, well, we'll be using both these for this next problem. So I'm gonna go ahead and let's go ahead and snip the formulas again and put it above the example. Okay, so this particular problem, we're asked, well, we decide to invest $8,000 for 6 years, and I have a choice between two accounts. The first account pays 7% per year compounded monthly. Okay, so if it's being compounded monthly, we're going to be using Formula 1 here. The second pays 6.85% per year compounded continuously, which is a better investment. So looking at this, admittedly, well, I'm giving it away, I guess, but I thought that the continuous compounding would pay out better. But I guess that's tricky how math can be sometimes. But 6.85, yes, it is lower than 7%, and honestly, now that I think about it, it is kind of substantial. Um, but we're just gonna figure out, okay, so which one of these accounts pays out better? All right. Lucky for us, we have these formulas. So let's go ahead and begin this. So we'll just say we'll correspond Formula 1 with account 1. All right. So let's go ahead and do that. So we're just gonna say 1. Okay, so Formula 1 and Account 1, luckily they do correspond. It says you decide to invest $8,000 for 6 years. So my A, the amount, what am I going to have at the end? All right, it's going to be equal to, all right, my principal that I'm investing is $8,000. And then it's 1 plus, my rate is 7%, 0.07. 7's looking awful here. There we go. 7%. All right, and it's compounded monthly. Well, how many months are there in a year? It would be 12, so we're going to put 12 for that. All right, and then again, I'm just simply following this formula here, and then raise to the nt power. So n again is the amount of times that I compound per year, so it's going to be 12 times, and then how many years here? Was said 6 years. So doing this formula, or putting this formula into a calculator. Oh, here we go. We got all right, so end up with $12,160.84. Okay, so after 6 years, my account has grown. That's pretty darn good actually. Um, my account has grown $4,160. Okay, so that's good. All right, well now we're gonna do account 2, and the arithmetic here is gonna be so much easier. Okay, so the amount is equal to my principal again, which is 8,000. All right, P, and then E. Remember, E is not a variable; it is a number. So we're just gonna keep that there. My rate equals is 0.0685, and then again times 6. So putting this into the calculator, we have $8,000 times E raised to the 0.0685. Little input error there, times 6. All right, so I end up with $12,066.60. Okay, so looking at these two accounts, I mean they're pretty darn close to one another, right? I mean, well, I say that. I mean it's almost $100 difference, but obviously the first account is the better account, and that's the account that I would choose. Now, like I said, $100 is pretty negligible right now, but imagine, you know, next up, this amount now gets compounded, and of course, the higher the number, the better the compounding is. So, even though it is a little negligible, in the end, depending on how long you keep it in there and how big the account is, the money does grow a lot quicker. All right, so now we're going to talk about present value. So, all present value is kind of the thought process is kind of reverse from the previous problems that we've been doing. The previous problems that we've been doing have been along the lines of, okay, so if I put in this much money at this interest, what will I have in the future? Now I'm running it backwards. All right, I'm saying, okay, this is the money that I want in the future. How much do I need to invest in now? In one moment, getting a little froggy there, and again, the same as before. It's just simple plug and chug. Now I know I keep saying that, but it really is not. There's nothing really to figure out. The hardest part to figure out. The hardest part about these is figuring out which each one of these variables are: P, A, R, N, and T. But again, that's not difficult. The difficult part, I believe, is going to be when you put it into the calculator. And I say that because twice in this lecture, I won't say I messed up on the calculator, but I my my parentheses is right next to my six, and I went to hit the six and hit the parentheses. Um, it happens. I think to me, I think that's the hardest part of this. But let's go ahead and begin this. So calculating present value, how much money should be deposited today in an account that earns 6% compounded monthly so that it will accumulate to $20,000 in 5 years? Of course, we think it was this class. We kind of had a problem like this before. I think it was about like the savings account, the birthday. They had a granddaughter. I think it was this class. Um, Kind of same thing. So let's go ahead and um, mark down which variables that we know. Okay. Well, we obviously don't know P, right? Because that's what we're trying to figure out. Where we're trying to figure out how much I need to invest right now, right? But I know that in the future, I'm going to want $20,000. Okay. Let's see. Um, we have an interest rate of 6%, so my rate is going to be 0.06. That's my rate. We are compounding monthly, so how many months are there in a year? Well, there are 12. And then my time frame here was 5 years, so t is equal to 5. So my formula is now going to look like this. So P is going to be equal to my amount, which is 20,000, one more zero, all over 1 plus my rate, which is 0.06, all over n, which is 12, raised to the nt, which is 12 times 5. And let's plug this in. Whew. Okay, so I got 14,827 and 44 cents. And 44 cents. Okay, so if I'm again, I mean, the example previously about savings account for a granddaughter, that makes a lot of sense. Um, so again, if I want my granddaughter here to have $20,000 in an account 5 years from now, then I would invest $14,827, and that's what the present value does. We figure out how much we need to invest in order to get the value that I want in the end. Again, it kind of works backwards from everything that we've done so far. Okay, so effective annual yield. Um, One moment. Okay. All right. So effective annual yield. More kind of vocabulary to gnaw on here. Let's go ahead and snip everything. That's not too much. Hopefully the problem will fit. All right, so the effective annual yield, as we've seen before, a common problem in financial planning is selecting the best investment for two or more investments. For example, in an investment that pays 8.25% interest compounded quarterly, better than one that pays, I'm sorry, I forgot the is an investment that pays 8.25% interest compounded quarterly better than one that pays 8.3% interest compounded semi-annually? So another way to answer the question is to compare the effective rates of the investments, also called their effective annual yields. So we did a problem like this earlier. It was example 3. Now it's just, well, I won't say just as easy, but I mean, we went ahead and did the arithmetic for both accounts to figure out which was best. Okay, well, in this particular case, we're not going to have to necessarily figure out both of them. We just have to figure out what, or not what, but how much one account is going to be paying me, and then compare it to, all right, well, my other account needs to pay, this X amount in order to compare, right? And I just was kind of wordy there, so let's just begin. Uh, so the effective annual yield, or the effective rate, that is a simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest at a stated rate. Again, well, let's just do the example. So we're going to deposit $4,000 in an account that pays 8% interest compounded monthly. We want to find the future value after 1 year. And then B, we want to use the future value formula for simple interest to determine the effective annual yield. So in order to begin this, let's just go ahead and do it like I've done every time. We're going to write down what our variables are. Okay, so in this particular case, we deposit 4,000, so that's going to be our principal. And again, we're not doing the future value. So let's go back because I think this could be kind of confusing. When we did future value, all right, or I guess it'd be present value. Sorry, present value. Whenever we calculate present value, we had the principal be the one on the left. Okay, because that's how much we want to figure out how much will happen, or how much will be in our account after so long. Okay, again, to reiterate, if we deposit $14,827 in 5 years, we'll have $20,000. All right, so present value flips A and P. All right, we're not doing that again. Instead, now we're going to be going back to our P being our present value, as well as our principal rather, and A being the amount that we're looking for. So P again here is $4,000. Interest rate 8%, so 0.08. Compounded monthly, so again we're going to be looking at N is equal to 12, and I think that's it. Okay, so A reads, find the future value after 1 year. Well, our formula was A is equal to P times 1 plus R over N raised to the NT. Okay, so again, looking at this, we in the original problem here, like without even looking at A or B, we were given these three variables. Okay, we'll look at the formula. I've got 1, 2, 3, 4, 5. Okay, well, A gives me my fourth one, which is after 1 year. So T is going to be equal to 1. So we do our formula. We have A is equal to my principal, which is $4,000, 1 plus my rate, which is 0.08, all over N, which is 12. And then NT was pretty easy, right? 12 times 1 is just 12, but we'll put that times 1 there. And more calculator work. All right, so looks like we're gonna have $44,331.99. But that 99 rounds up. So we're going to say $4,332. Okay, so after 1 year, I'll have $4,332. Now B reads, use the future value formula for simple interest to determine the effective annual yield. So now we're going to have to use that formula on the previous page. Well, no, let's find the future value formula. Use the Oh, yeah, okay, so we just have to do simple interest here. Alrighty, so my simple interest that I have to do is just going to be, I guess we'll use yellow again. Actually, do next page. My simple interest formula, if you recall, we're just going to be A is equal to P times 1 plus NT, or RT. All right, this is my simple interest formula. And so again, this problem to me, I think, is worded just a little weird. But again, I'm just trying to figure out. Okay, I need to figure out what the interest rate on a simple interest formula is that would match this that would match these parameters here. If I wanted to find the value after 1 year that pays 8% interest compounded monthly, I want to figure out what would be the simple interest of a normal account that would match getting this return. Okay, so again, just simply plugging everything in. All right, I'm just trying to figure out the rate now here. Okay, so yeah, I'm just trying to figure out the rate. So my amount was 43.32, I believe. 32. Yeah. Okay. And then what was my original amount I put in was $4,000. All right, 1 plus my rate. Again, my rate is what I'm trying to figure out. And then T, which is 1, so that's pretty easy. So it's just going to be R. So I'm just going to try and solve for R. Right? And doing this, we're going to have, I probably shouldn't have written it so big. Let me erase this so I can try to keep this all on one page. Okay. And again, I'm just going to go ahead and write the 1 plus R because my rate, we don't know, and my R was time of a year. My R's aren't really working. There we go. All right, so my math here, just solving for R. Okay, so what I did here was I distributed the 4,000, and that's where I got this. Then I'm going to subtract both sides by 4,000, so I'll have 332, I'm sorry, it's equal to 4,000 R. Now I'm going to divide both sides by 4,000, and that will give me my rate. So divide both sides by 4,000, I've got 332 divided by 4,000, that's equal to my rate, which is going to be equal to, and this is the easiest calculator work I've done all day, 332 divided by 4,000. All right, looks like, so it is 0.083, or in other words, 8.3%. Okay, so I'm going to let the textbook take over here and word it a lot better than I feel like I could have. Current page. Okay, so the effective annual yield or effective rate is 8.3%. That's what we got here. This means that monthly. This means that money invested at 8.3% simple interest. Again, that's what this formula is. simple interest, earns the same amount in 1 year as money invested at 8% interest compounded monthly. Okay, so what we're doing, again, we're just figuring out, okay, so this is the money I get compounding it monthly. What rate do I have to have in order to compound it continuously to match that? And well, it's 8.3%. Okay, and then lastly, we're going to talk about uh, calculating effective annual yield. We're going to assume that there are 360 days in a year. Alrighty, so generalizing the procedure of example 5 and checkpoint 5 gives a formula for effective annual yield. So suppose that an investment has a nominal interest rate R in decimal form and pays compound interest N times per year. The investment's effective annual yield Y, again in decimal form, is given by our formula here. The decimal form of Y given by the formula should then be converted to a percent. That's kind of what I did here at the end here, right? I took this decimal form and converted it to a percent. That's what we're going to do also at the end of this. So in order to figure this out, again, we're just going to plug stuff in and put it into the calculator. So a passbook savings account has a nominal rate of 5%. The interest is compounded daily. Find the account's effective annual yield. And again, we're going to assume 360 days in a year. So what we're going to do is figure out, okay, so what variables go where? Well, we're trying to figure out what big Y is, so we're not going to write that over here. But our our rate here, it was a nominal rate of 5%, so 0.05. The interest is compounded daily. Well, in how many days are in a year? Normally there's 365, but this is wanting us to put 360. And that's it, right? That is actually all the variables, because the other variable, the big Y, is what we're going to try and figure out. So we've got Y is equal to 1 plus my rate, which is 0.05. I'm always having to erase my zeros and rewrite them. I don't know why I can't close them. Over N, which is 360. And then we're going to subtract 1. Okay. So doing the arithmetic here, it's going to get a little dicey, I think. So 1 plus 0.05. Oh yeah, there's an N in there. Sorry about that. Thank you. Plus 0.05. Okay, so that's the section wasn't as bad as I thought it was. So just doing the arithmetic here, I have 0.05. I don't know what it's wanting. We'll go to two decimal places here for this. 512 or 513. So 513. All right, and of course that's equal to 5.13%. Okay, and again, what does this mean? Well, in order for, you know what, let's just do this. I feel like I've been rambling a lot today. Okay, so at least they went out to two decimal places, which makes sense, because if I would have stopped at 5%, then that would have been the exact same, wouldn't it? Okay, so the effective annual yield is 5.13%. Thus, money invested at 5.13% simple interest earns the same amount of interest in 1 year as money invested at 5% interest, which we have here, right? The nominal rate, or compounded daily. And I believe, yeah, that takes care of the last example here. Just a quick recap of this particular section. It really is just, and I'm pretty sure you're given the formulas, but just take the formulas, plug the values in, and proceed. That's it. That concludes today's lecture. Does anybody have any